and thank you for joining us today. So in this session, we'll show how you can build your first AI-ready graph application in under 30 minutes. Now, many graph and AI projects tend to stall early. This is not because the use case isn't clear or doesn't have value. They stall because teams just get stuck early during onboarding, data setup, schema design, infrastructure configuration, and this happens long before teams see any value. So our goal today is simple. We're going to show you how quickly you can go from an idea to a working AI-ready graph application using TigerGraph Savanna. And by the end of this session, you'll have a concrete understanding of what AI-ready means in practice, and how fast you can actually get there. So we'll start by grounding this session in reality, in the reality that many teams experience. Why graph and AI initiatives often stall, even when the use case and business value are clear. From there, we'll look at how Savanna directly removes the onboarding friction that causes many of these projects to slow down or stop, and getting teams to create a working graph instance much faster. Next, I'll step back and explain why Savanna is able to do this with a high-level review of the architecture and the design choices that make it scalable and AI-ready. And finally, we'll spend the rest of our time on a demo where we'll show how quickly you can provision a working AI-ready graph application using Savanna. All right, so what are some of the challenges that teams experience with graph initiatives? So in practice, we see four recurring challenges that slow graph initiatives down. The first is that graph introduces a fundamentally different way of thinking than relational systems. Teams are no longer modeling tables and joins, but relationships, flows, and behavior over time. And in many cases, they're modeling business processes, payments, onboarding, fraud, identity, and those processes don't always translate clearly into graph patterns without prior experience. Second, once the teams understand how to model their data, the next friction point is getting the data into the graph. Now, in enterprise environments, data fragmentation is expected. That's not where the challenge lies. The real challenge is the effort required to connect data sources and shape them into a usable graph. Building and maintaining data pipelines typically requires custom development and ongoing operational effort. And that effort increases further when teams integrate graph data with ML, GNN, or LLM pipelines. Now, third, teams often struggle setting up the infrastructure and security required for graph initiatives. So before they can validate a use case, teams are forced to work through provisioning, security reviews, access controls, and environment setup. Now, this early operational friction slows momentum and pushes time to value further out. And finally, even after onboarding, scale becomes an issue. Deep traversals over highly connected terabyte scale data push many systems to their limits. AI-driven use cases in particular raise the bar further. They require predictably low latencies and high performance in real time. So the goal here is simple. We want to accelerate the time it takes to get to a working AI-ready graph application. And that's where Savanna comes in. To close the skills and mindset gap, Savanna starts with solution kits. Instead of a blank canvas, teams begin with predefined schemas based on real use cases like fraud or entity resolution. The data is already connected, so relationships and patterns are immediately visible. And starter queries and algorithm libraries shows how to ask graph questions and validate ideas quickly. And Savanna comes with 9 pre-built solution kits. So there is a solution kit for many use cases. Uh, to reduce the data integration effort, Savanna focuses on fast, no-code ingestion. So pre-built data connectors expand what teams can bring into the graph without the need to build and maintain custom pipelines. And then we have MCP guided ingestion and automation that makes it easy to convert and ingest tabular data into a graph. To simplify setup, infrastructure, and security, Savanna is fully cloud native and managed. Savanna streamlines onboarding and initial setup with built-in isolation, access control, and environment management, so teams can focus on use cases instead of infrastructure setup. And finally, Savanna is designed to be developer and AI friendly from day one. We support multiple query language, which lowers the barrier to entry. Graph and vector workflows, including GraphRag, are supported out of the box. The algorithm library enables feature generation for ML workloads, and native integration points allow graph data and features to plug directly into ML and GNN pipelines. And the result is faster movement from exploration to validation and from validation to production. Now, Savanna is fundamentally built differently from traditional graph platforms. It's cloud native by design. It's not on-prem system that was later moved to the cloud. And from day one, it is designed for scale, performance, and AI workloads working together. So one of the key architectural difference is the independent scaling of compute and storage. This allows teams to scale query performance, analytics, or inference without duplicating or moving data. It also enables more efficient cost and resource management as workloads evolve. And Savanna is optimized for high performance graph processing. Deep traversals over highly connected data are a core design point, not an edge case. And this is critical for use cases like fraud detection, entity resolution, and graph-powered AI. Predictable performance is also essential for production AI workloads. And Savanna delivers consistent, low latency performance for real-time queries and AI-driven applications. So teams don't have to trade off scale for responsiveness. And finally, Savanna supports operational flexibility across the full application lifecycle. Workloads can be deployed, paused, resumed, or retired as needed. And this allows a team to experiment, validate, and scale without long-term infrastructure lock-in. So next, I'll show how these architectural choices translate directly into Savanna core concepts. So let's take a look at the Savanna architecture. At the top of the diagram are the ways users and applications interact with Savanna. So you have the cloud portal, tools, insights dashboard application, REST APIs, and integrations with external systems. This is the entry point for developers, data teams, and AI applications. On the left-hand side is the control plane managed by the Savanna controller. This is where provisioning, lifecycle management, security, and orchestration live. It's also where solution kits and the graph algorithm library sit, which is why onboarding can be guided and repeatable instead of starting from scratch every time. On the right-hand side is the data plane, which is intentionally split into compute and storage layers. So starting with the compute layer, graph services run on Kubernetes using EKS, and that gives Savanna elasticity and containerized compute. And this is where queries, graph algorithms, analytics, and real-time workloads actually execute. Observability is also built in through Prometheus, FluentBit, and Grafana, so performance and health are visible by default to users. Below that is the storage layer. So the graph data, vertices, edges, and properties is persisted in TigerGraph database, backed by cloud-native storage like EFS and S3. Storage is independent of compute which means that data stays put even as compute scales up, down, pauses, or changes. And the key takeaway here is that compute and storage are fully decoupled, which means that Savanna can run multiple workloads against the same data, scale performance without duplicating data, and deliver predictable latency for real-time and AI use cases. And so this architecture, it really is what enables everything you're about to see next in the demo. So one of the most important architectural choices, as discussed, is the separation between between compute and storage. This goes into a little bit more detail. So at the bottom of the diagram is the storage. It's the persistent layer that holds the graph, and it remains intact regardless of how compute is started, stopped, or scaled. On top are workspaces, which provide the compute layer. So every graph has a read-write workspace, which is required for loading data and modifying the graph. This includes data ingestion, transactional updates, running queries, and writing features or results back to the graph. The read-write compute is elastic. It can be paused, resumed, resized as needed, depending on ingestion volume or write activity. And then there's also a read-only workspace, and those are optional, and they're used to separate the workloads. They allow teams to run exploration, analytics, or inference without competing with write activity for resources. And this is especially useful when you have read-heavy workloads that needs to scale differently than graph updates or data ingestion. So both read-write and read-only workspace attach to the same underlying storage. That means that multiple workloads can operate on the same graph without data duplication or data movement, or even the requirement to multiply the storage volumes at cost. So the result is predictable baseline cost for storage with flexible usage-based scaling for compute workloads. So here we see how this compute storage separation is implemented concretely in Savanna. So you're using three core concepts. At the top, you have the work group. So the work group defines the logical boundaries of an environment, region, isolation, and security. It doesn't run queries. It doesn't store data. It simply governs and scopes what lives underneath it. On the left-hand side is the database. This is the persistent storage layer where the graph lives. And the data remains intact, as we mentioned, regardless of how compute is scaled, paused, or removed. On the right-hand side are workspaces. Workspace is an in-memory compute layer where queries, analytics, and algorithms execute. Workspace can be created, resized, paused, resumed, or retired independently without affecting the underlying data. So you have full lifecycle management there. Now, each database has a single read-write workspace attached to it. This workspace is used for data ingestion and is elastic. It can be scaled, paused, or based on the write activity. And in addition, you can also attach multiple read-only workspaces to the same database. So those are used for querying, analytics, AI inferences. And because read-only workspaces are isolated from write workloads, they don't compete for the same compute resources. All right, so now let's jump into we'll dig a little deeper into why graph is so central to AI workloads. So most enterprises store vast amounts of data. So think transactions, users, devices, merchants, events. What's missing is connected context and the ability to reason across it. And graph provides both. As the data moves from table into a graph, so from the left-hand side of the slide to the graph, two important transformations happen. First, distributed data becomes connected. So data that previously lived across separate systems, tables, and streams is then unified into a single shared data model. There is no need to rebuild joins at query time, create pipelines per use case, or duplicate logic across teams. The result is a reusable data foundation that multiple applications and models can build on. Second, relationships become explicit and first class. So in tabular systems, relationships are implied by keys. They're reconstructed repeatedly by every query or model. In graph, relationships are explicitly modeled, they're persisted, they're traversable, and they're explainable. And so the context is preserved. It's not flattened, it's not lost. So this matters because most AI failures are not model failures, they're context failures. So models fail when they don't understand how entities relate, how behavior evolves over time, or how signals come across different systems. Graph makes connected context native. It enables reasoning over multi-hop relationships, temporal patterns, and behavioral flows while remaining explainable. So once data is modeled this way, the same graph foundation supports multiple AI use cases without reengineering. So for example, fraud detection uncovers collusion, neural networks, and risk patterns. Entity resolution works across noisy, incomplete, and conflicting data. Hyper-personalization improves by understanding users in context, so relationships, behaviors, and history. Digital twins model real-world systems as evolving networks of entities and interactions. And GraphRag grounds LLM structured, connected, and explainable knowledge. All right, so now we're going to make this concrete with a demo. So the goal is to show you how quickly you can build a working AI ready graph application in Savanna without weeks of setup or custom plumbing. We'll start by creating a new Savanna environment in just a few minutes. Then we'll deploy a solution kit, which immediately gives you a predefined schema, connected data, started queries out of the box. And then from there, we'll look at how the schema is structured and how the data is already modeled as connected entities. And then finally, we'll explore the graph using no-code tools to surface patterns and insights directly from the data. I'm going to switch over. So we'll first have a short video. And we'll start by creating a brand new instance in Savanna from scratch. So the first step is registration. So I provide an email address, I create a password and click on continue. Savanna will then send me a confirmation email, which I accept. I'll also accept the terms and conditions and move forward. Okay, now I'm asked for a few additional details, first name, last name, company, role, and how I intend to use Savanna. When that's complete, Savanna starts building the instance. So this can take a minute or two. Once the instance is ready, I'm given a few options on how to proceed. And in this case, I'll explore on my own since I want to show how to build a system from scratch. So once in the product, I switch to the light background. I create a work group. I give a work group name. I select AWS as the cloud provider in the region. And then I'm also creating a workspace and a database. And as part of that setup, I'll select the transaction fraud solution kit, which means that Savanna is not just creating the work group, workspace, and database. It's also loading a predefined schema, connected data, and starter queries for fraud detection. So as you can see, this process takes about 8 minutes end to end. So you can see the timer there with the progress bar. But within that time frame, I will have set up a Savanna instance from scratch. I will also have loaded a solution kit that includes uh, the schema, preloaded data, and queries. And so we'll see how powerful the solution kits are as we jump into the product. So we'll switch to the actual product. All right, so here is the Savanna instance. You can see the workspace we just created. It's a read-write workspace, and it's connected to a database. Since we loaded the transaction fraud solution kit, the first thing I'll do is to look at the data profile. So I can have a list of the solution kit here that's loaded. You can see that it installed the transaction fraud solution kit. And if I look at data profile, now this is where I can immediately see what was loaded. So there's about 873,000 vertices, 2.8 million edges. Now, because this is a transaction fraud data set, most of the vertices represent payment transaction. You can see the vast majority here. You also have a tabular data here that will show you the individual vertices and the edges as well. Now, the edges show how those transactions are connected to merchants, to cards, and other entities. And so this gives you a quick high-level view of what is contained in the graph and how the data is distributed. So now let's take a look at the schema. Here's my schema. So this is, again, fraud schema. It's centered around party vertex right here. You can see that that's the central vertex. It has all of these other nodes connected to it, including date of birth, IP address, phone, email, full name, device, and of course address. Now the party, think of the party as the consumer or the card holder in this use case. And the parties are also connected to cards here, which is then connected to both merchants and payment transactions. All right, so this is how all of this data is connected, and the edges show the relationship. And those relationships are already modeled and they're persisted in the graph. So when you think about this data here in a relational world, this data would span many tables with joints across transaction, customer, devices, and merchants. And some of this data may actually reside in separate systems, right? You could have customer data in, let's say, a CRM system, and then transactional data in an ERP system. So what's different here in the graph is that all of this data is centralized, it's unified, and it's designed for deep traversal and analytics. And all of these relationships are already modeled, they're persisted, and they're explicit as well. All right, so now let's see how easy it is to explore this data without writing any code. So I'm moving to our Explore Graph application. And from there in the bar here, you can see that I can see all of the vertices that exist in the schema. So given this is fraud transaction, I'm going to pick the payment transaction. I'm going to filter the data here. I'm going to add a filter. You can see that I can add edges to other vertices, but I'm going to first add a filter. These are my attributes for these payment transactions. So I'm going to look for transactions that are fraud equals to 1, which indicates a fraudulent transaction. And the other thing I'm going to do is I'm going to look at how those payment transactions are connected to merchants. So I'll pick this option here. And then I'll set my query parameters. I'm going to limit it to, let's say, 10 results, and then I'm going to go ahead and run it. Okay, so here I see different merchants that are actually connected to fraudulent transactions. You can see I was able to essentially, with a few clicks and no code, create what essentially is a query and explore the data very quickly and very easily. All right, finally, let's move to the query editor. This is where preloaded queries and graph algorithms live. You can see here that the graph data science library includes different classes. So this is the graph data science library. It includes it's included out of the box. There's 50 algorithms that are available. And it covers different classes of algorithms. So you have centrality, classification, community, graph ML, path, similarity, and link prediction. And each of these have specific flavors for each of these algorithms. Again, they're available out of the box, which means that you don't have to start from scratch. In addition to the graph data science library, you have queries that are specific to our schema, the schema that was loaded with the fraud detection solution kit. Here you have queries about merchants and transactions. You also have queries like weakly connected components. You have PageRank queries. It's really expensive in terms of all of the queries that are available to search the data. So again, what happens here is you could start with a set of queries, a schema that's defined, preloaded data, and you can modify all of these to meet your own needs and your own data set. All right, so the key takeaway from this demo isn't to go in depth in any single feature, but it's really to show you how quickly we got there. All right, in just a few minutes, we went from nothing to a fully provisioned environment that's loaded with data, a meaningful schema, and the ability to explore and analyze the graph, all without custom code, all without having to build a pipeline or do a heavy setup. It just took a few clicks and several minutes. And that's really the value that Savanna is designed for. Alrighty, so let me go ahead and switch back to our slides. Okay. And really, this was this concludes our today's webinar. We want to thank you for joining. If you would like to experience TigerGraph firsthand, you can start with a free trial of Savanna at tgcloud.io, or you can simply use the QR code on the screen here to launch your own Savanna instance in minutes. And you can replicate what we just went through in your own time at home. You can also try different solution kits. Again, we have 9 to choose from. So the choice is yours. Savanna does come with credits, so you could actually try it for free.